Welcome to our workshop. Please let me point out that I appreciate that you took your time to spend your lunch with us. For me, it's the third time that I'm doing this kind of workshops here at the ARC conference. 2 years ago, at this workshop, I introduced something we called the security environment for functional safety. Meanwhile, there is an official technical report published by the IEC describing what is meant by the security environment for functional safety. Last year, I stood here and talked about the possibility to utilize hard functionalities when actively accessed by the safety controller to improve loop checks and commissioning activities. We're actually in the situation that we're completing the first projects where we do this extensively. And today, I'm planning to strive with you a little bit through a number of different aspects. All of them are related to functional safety. A lot of them are related somehow to security. And the overall credo is the question, what is the meaning of IoT or Industry 4.0 for functional safety, and what do we need to do in order to be prepared for IoT solutions? If you're taking a closer look to what is stipulated in the IEC regulations, we can find this schematic here. In this schematic, you can see that on one hand side, the process risk is defined as the product of consequences of a hazardous event and the frequency of the occurrence of such hazardous events. And typically, the residual or the initial process risk borne by that need to be mitigated so that a tolerable maximum risk can be achieved. If you look at the understanding of the people doing the safety standards for the process industry in the IEC, there should be different layers of protecting the applications. And if we are trying to understand what that means, we can say, okay, we can understand the process equipment as a kind of a disk that is attached to a shaft, and the shaft is slowly rotating. And in this disk, we have some holes, and these holes are representing potential failures in the process. In fact, the diameter of the holes and the count of the holes are representing the error probability. And you may understand it in such a way that there are transmitters and receivers, and whenever a hole is passing by the area between transmitter and receiver, this is a malfunction in the process. Whether this malfunction may have consequences or not is depending on the timely criticality of the individual malfunction. That means, for instance, if you have a large tank and your level gauging system may not deliver accurate values for a second or two, nobody probably will care about. If you have a flame monitor in the furnace and the flame monitor in the furnace will not deliver accurate values for 10 minutes, you probably are in trouble. So this is depending on the individual timing. In order to cope with these deviations and this, in order to keep control about them, a second disk is attached to the same shaft, representing the BPCS functionality. And this disk is at the same shaft, is rotating in the same direction, but with a different RPM. And the idea behind is that events triggered by the holes at layer 1 may be covered by actions in layer 2. And this is what we call, at the end of the day, basic process control solutions. Now, unfortunately, this layer of the basic process control solutions also has its holes. And the key question here is, what if two holes simultaneously are at the same point? And of course, what if the consequences and the residual risk of such a situation are not acceptable? Well, the answer is relatively easy. In that case, or for preventing this case, we attach a third disk to the same shaft, that is causing an additional risk reduction. Of course, also this disk has its holes, but the idea behind is that these holes are much smaller, and the amount of holes also is much smaller than it is, excuse me, than it is in the basic process control system. The aim of this setup is that we achieve a risk reduction that allows us to bring back the initial risk to an acceptable level. Having this said, who of you knows why ZIL 3 is called ZIL 3? Why ZIL 3 is called ZIL 3? Yes? ZIL 3 is called ZIL 3 because such a solution is able to maintain a risk reduction of at least 1,000 and maximum a little bit less than 10,000. Because 10,000 risk reduction factor of 10,000 would be ZIL 4, right? That means the ZIL 3 system, and this is what we are typically talking about, is intended to maintain a risk reduction that is higher than 1,000. Risk reduction, maintaining a risk reduction higher than 1,000, what does it practically mean? Mark?
Quick question. So you have two variables, your EPCS and SAS, but there can be, you're just showing two examples, right? There's many other types of.
Yes. I'm not talking about the non-SIS safety functions that you also may attach, and I'm not talking here about the additional mitigation systems such as fire and gas systems, but also organizational measures, because somehow our focus is SIS, right? And for reasons of simplicity, I try to limit this to 3 layers here. Now, ZIL 3 means that if we are talking about a low demand mode system, the maximum demand rate is 1 demand per year. That is what the standard says. And ZIL 3 in this meaning means that such a system is accepted to dangerously fail once 1,000 years, right? And that means on one hand side, we have to think about what is the technology level we have to apply in order to achieve that. But what is even more important, what is the level of the quality of the engineering we have to achieve in order to maintain such a reliability on the systems. And I will come back to that in a moment. Now, if you're looking at the impact of IoT, or Industry 4.0, how we call it in Germany. At the end of the day, we can say, okay, the complexity of the basic process control solutions will grow. The security constraints to be taken into consideration will be increased. The speed of changes also will grow, because one of the ideas behind Industry 4.0 is that you easily can change more or less all functionalities. And unfortunately, this increased speed will lead to the situation that our holes we were aware of in the BPCS layer also will grow. And we may understand this as like attaching an additional drive to the disk representing the basic process control system and increasing the speed of the rotation on that. Now, what do we do for the safety instrumented systems? For the safety instrumented systems, we typically have a pretty static setup. And if you're looking at the engineering processes, there is a lot of manual rework to be required in order to implement changes. So this is a little bit like we have a hand crank in our hand when talking about changing the SIS, while the BPCS is driven by a motor. The question, or one of the key questions, is how to increase flexibility, how to make sure that what we do in terms of functional safety is more flexible, is more easy to be adapted to changes. And one of the ideas is that we may say, okay, let's make sure that the motor that is driving the BPCS disk also is driving the SIS disk. But if we do this kind of integration, then we have the problem that we, of course, are getting much more flexible, but we're also getting far less safe, because on one hand side, the diameters of the holes in the BPCS as well in the SIS are getting bigger. And secondly, if you do this kind of coupling between the two devices, then the systematic errors that can be covered by different technologies, if the systems are not integrated, cannot be covered in that way anymore. That means instead of having two independent layers, in this situation you're creating one layer. And that also means that in this one layer situation, the common cause or the commonly used elements, such as operating systems, such as network protocols, such as dedicated microelectronic systems, need to be able to comply with the sum of the risk reduction of the two layers that were existing before. And that practically means, if we say, and the IEC 61511 says that for the BPCS we can claim a risk reduction of factor 10, and for the SIS in ZIL 3 level we can claim something between 1,000 and 10,000, that the overall risk reduction of such a system where common cause failures need to be considered, need to be able to cover risk reductions of more than 10,000. And that means ZIL 4, right? And this is an important technical burden of which not that many people really are aware of when talking about the application of fully integrated systems. Now, nevertheless, the situation exists, and we need to think about what we need to do in order to get ready for the implementation of IoT solutions, right? Because if there are difficulties and if there are certain systematic constraints to be considered, that should not hold us back from doing these things. But we need to think about, first of all, what we want to change. Is it what we do, or is it how we do? Now, because these are always the aspects to be considered. If you have to implement new strategies, excuse me, you always may think about what is it you have to change compared to your existing practices, and of course also what need to be changed in the how you implement your practices. And from our point of view, based on the experiences we made during the projects we implement, we firmly believe that if we want to support IoT compliant flexibility and also IoT compliant workflows, we have to review both. We have to review what we do as well as how we do. Let's take a closer look at what we do. At the moment, if we're following IEC 61511, we have to follow a workflow like this. That means in the beginning we have to do a process hazard and safety analyze. We have then to do a layer of protection analyze. We have to do our safety requirement specification. We then enter into design and build phase. We test and maintain. Finally, we operate these systems, and then a dedicated management of change need to be implemented. All this has to be governed by a dedicated safety planning and by the implementation of a dedicated assessment and audit trail. Now, if you're looking at the similarities and the differences, what we can see here is that only design and build of the safety systems is more or less identical when talking about the correlation between BPCS and SIS. There's a lot of activities we have to undertake where which we only executing for SIS, right? Things like the risk analyze, the LOPA, and the SRS only are done for the safety systems. And we have some activities such testing and maintenance, such operations, but also management of change, where we may come to the conclusion that the system, the processes applied for the safety systems are similar to the basic process control systems. But if you're taking a closer look to that, we easily can find out that there are major differences in the details of these processes. So from our point of view, the takeaway is, first of all, SIS engineering, if you look at the entire workflow, is not like BPCS engineering. This is a dedicated workflow, and if you look at how we can drive efficiency and how we can do the things more flexible, one of the important things is that we have to understand the engineering steps making up the engineering activities related to an SIS as one integrated workflow, with a focus on functional safety. We see that there is limited overlap between the things we do for functional safety and the things we do for basic process control. And if we strive for more efficiency, we need to understand this as one integrated process dealing with functional safety. The second element is how we do. And if we look at today's practice, what happens is, in the beginning of the phase, we have the determination of the hazards. We then enter into a LOPA, and then from there, we have the different activities for the non-SIF, like mechanical protection layers. We of course have the SIS, the SIF safety requirement specification, but we also have other non-safety aspects to be considered, such as security, for instance. I think yesterday and today we heard, or I heard quite a lot of times people saying there need to be a risk management for security purposes. If you're talking about risk management, why not harmonizing all this in one dedicated workflow? Because the principles, whether we are talking about process safety or we're talking about security for process applications, are not that different, right? Looking at the tools used these days, typically specific tools are used. Most of them are somehow handmade, if you allow me to say it that way. For hazard and risk analysis and LOPA, quite often different tools are used. And of course, non-SIF, non-safety, and SRS are done differently. If we then go one step down the road, the next step is the equipment qualification and the functional qualification. And actually, we see this quite often done per project. That means for every individual project, you start qualifying your equipment, qualifying the functionalities you use for safeguarding a dedicated product. Typically, no specific tool is used for that. There's a lot of different documents in different formats. And last but not least, this very often is done in a phase of the projects where there's no clear understanding present yet for the maintenance procedures that have to be followed once the plant is in operation. And then we enter into design and build, validation and operation. There we mainly using the same principles like we find for the BPCS. We have then the maintenance and test activities. Those typically are executed using the ERPs in place, because you typically will have an ERP system for managing your maintenance activities. And last but not least, a management of change process is in place, but this management and change process typically is executed manually. This is how we handle, or we see how safety installations are handled these days very, very, very often. Now, if we look at the question how we can do this more efficiently, the first thing is that we believe we need to use a platform-oriented tool covering all aspects of safety. That means one tool where you can determine your hazards, where you can do the LOPA, where you can do the safety requirement specification, but also all the specifications for the non-SIF, but probably also for the non-safety aspects of a plant operation, where you can have access to pre-qualified functions, to pre-qualified equipment, and from where, by using dedicated functional libraries, can automatically transfer the functionality on the engineering tool or to the engineering tool of the safety systems. So that instead of having a lot of independent individual tools and documents, you have one platform-oriented database system that allows you to, on one hand side, have all the information in one homogeneous system, have the possibility already during the engineering phase to have full control on the correlation between the hazards identified and the way the functionality that are used for covering dedicated hazards, so that you also can simplify your effort you have in terms of iterations you may need to go through. And based on that, on one hand side, reduce the man hours required in order to do such a complete process, and on the other hand side, improve the quality of what you are doing, because if you have the possibility to directly determine this is a dedicated function in a safety system, and this dedicated function refers on a dedicated hazard we identified, the entire review processes you have to go through with local authorities in order to get process licenses also are drastically simplified. Yeah, it is important here from our point of view that we have two layers here. We have the layer of information processing, where we are using such a platform-oriented tool, and we have the layer of functional safety, right? That means in our case, in the projects we execute, we use an engineering tool for the programming and the configuration of the safety systems that is safety related. So that means it's not such that only the controllers are safety related, but it's the controllers plus the engineering system that are safety related. And based on that, by using this kind of libraries, you can drastically minimize the testing effort, because that allows you to use pre-tested and pre-qualified library elements. Yeah, another important aspect from our point of view is then also that testing and maintenance are done using the same tool. And that means to have here automatically the possibility to capture the information about the operation of the safety systems. That means, is a low demand mode system really in low demand mode? Or do you have safety activations that are more often than applicable for a low demand mode? You have here then the possibility to enter also the results of the maintenance activities. That means if you anticipate, for instance, an average reliability of a transmitter that may fail only once per 10 years on average, you here have the possibility to automatically trace whether your equipment really reaches this reliability. And what you can do then here is to say, okay, on an enterprise level, we can define risk KPI, and we can automatically monitor whether the KPIs set for the behavior of the safety systems are met or not. And this, from our point of view, makes the difference between safety engineering and risk management, because here you have the possibility to identify what are the KPIs you're targeting for, and if these KPIs are met or not. And if such KPIs are not met, then you can actively take action in order to make sure that you get your operation to where it should be. And having this said, as already outlined earlier, this, of course, in the first place is done for the safety-related aspects. But it also can be done using the same system, using the same platform for security aspects, but also for resources and other risk drivers, so that you can have one enterprise-wide system where you can do your entire risk management. Yeah, the first important aspect here is that by applying this, we are covering the different life cycle phases of a plant. Because what we also see quite often, there is in the initial phase the capital investment. During the capital investment, the functional safety plan is done, the risk and hazard analysis is done, the LOPA, SIS are done, and design and commissioning is made. And then somewhere later, the operational phase is entered into, and here we then have the aspects of maintenance management, recurrent testing, performance reviews of the safety system, and of course, management of change, right? And in order to optimize the overall cost of safety, we need to strive for having the biggest overlap between both phases than we can get. And from our point of view, this is what we call safety excellence. And the question is how to maximize this overlap. And the concept we developed for that is what we call integrated risk management, where we are considering the aspects borne by the CAPEX phase of the projects and the OPEX phase of the projects. Now, how does it work out? Because these are nice-looking slides. But the question is how to do this practically. So what we did is we developed something we call the security zone for functional safety. Probably you may remember I was talking about this a few moments ago. In this security zone for functional safety, we have the safety-related hardware of the controllers. In our case, the different product families that are used in the same fashion. That means the security concepts for all the products are the same. In this security zone, we also have the engineering stations for the controllers, and we have the possibility to communicate to the outer world in two directions. In one direction, protected by a data diet. That means this is the communication path used for getting information out of the security zone for functional safety. But we also have the possibility to communicate in the other direction. We have here a specific device that either can maintain network communication to the outer world that is secured, or that can support the usage of portable memories, and it can administer such, well, as we call it, sporting shoe networks, where you have to hand carry portable storages. This is a little bit depending on what are the individual preferences of our clients. For that, we then attach the platform-based safety engineering tool. We as HIMA, for this kind of purposes, cooperating with Mangan Software Incorporation, who are providing a tool here called Safety Lifecycle Manager. This is the platform-oriented database system I was talking about earlier. And what we are doing here is that we are connecting these platform with the security zone for functional safety, and by that And this connection can either be done using networks, can be done using portable memories, can be done via the internet if required, because we have the possibility here to establish protected connections even through the internet. So this is at the end of the day depending on, or what is the preferable solution is depending on how the individual setup looks like and what are the individual preferences of the operating companies. By that we have one integrated tool where we can track the safety organization, the safety data required for running the application, the safety stipulations that need to be maintained, the safety background information, for instance, what kind of overrides are active, what kind of measures to be taken in case of activation of an override, and last but not least, a KPI monitoring system is supported by this solution. How do we do that? This is then in total what we call the IoT workspace for functional safety. Because the basic for the applications here is the usage of open communication technology. And this is our concept on how to implement IoT technology in order to make sure that we can get more flexible, that we can have safety installations that can be handled in a way reflecting the flexibility demands of IoT implementations. Now you may say, well, again, this looks interesting, but what is behind such a firewall? And what I brought with me here is a picture on how we do security for functional safety. So what we do is we have the core of our products. That is what we call the secure safety core. In this secure safety core, we do 99% of all the software development ourselves. That means we do not use commercial off-the-shelf software. All the software we use here is developed by ourselves, and we are relatively confident that this software is relatively stable and relatively free of errors. You may now say, what does relatively mean? Well, our customers at the moment are running something like 35,000 of our systems around the world, and we do not know about even one security-relevant incident. This may change tomorrow. I don't know what is going to happen tomorrow, but based on the historical track records, I'm a little bit self-confident here. Then around the safety core, we have what we call security environment for functional safety, and there we have the interfaces, the one that allows to import data and the one that allows to export data. For the one that allows to export data, we are typically using OPC UA. This is the philosophy on how we do safety and how we do security, and this is the way around we are attaching the security environment for functional safety to the platform hosting the safety engineering functionalities. Another important aspect is how to do the rollover from the information domain to the safety domain, right? We have the engineering platform, and all we do in the engineering platform is just handling information, right? That means the engineering platform as such is TÜV certified. That means the processes driven by the platform are in line with the IEC 61511, for instance. But of course, this platform is not safety related. So that means internal errors of PCs or networks may have an impact on the functionality. On the other hand side, when we convert this into functionality of the controllers, we need to make sure that under all circumstances, the functionality is like specified. So what we do here is we segregate this entire thing into 3 different elements. On one hand side, we have the pre-tested function library that is hosted by the engineering station of the safety system. And then we transfer the tag names of all the safety functions that are part of this project in one step into the engineering station of the safety system. In the second step, based on the safety requirement specification, we transfer what are the functional typicals and what is the assignment of the tag names to the individual functional typicals, also into the engineering station. And the engineering station that is safety related then is creating the application program by using the tag names and using the functional typicals. And in case of mismatches, an error message is reported, so that you can say, okay, we have 2 different ways of introducing or injecting the software into the engineering station, and on the level of the engineering station, then both sets of data are combined and are commonly processed. There's one further step, and that is that we also have the possibility to establish test plans. That means for each of the functional, for the functions defined in the safety requirement specification, a test plan is established, and this test plan then is also, in a third step, moved over to the engineering station of the safety system, and the engineering station of the safety system is able to operate a soft controller, and even the soft controller is safety related. And this validation program then is put into the soft controller, is validating the correct functionality, and if the validation goes positive, then a related document as validation evidence is generated, and this then is stored again in the engineering tool, so that you can say, okay, this was the functional engineering baseline, and this is the test program for the desired function, and in the final step you can store the validation evidence proving that all the functions worked correctly. Another important aspect is, and this was something I was talking about last year, what we also support is what we call smart loop check. Smart loop check means that if you have hard transmitters, the safety controllers having an integrated hard interface, and this integrated hard interface allows the controllers on one hand side to read diagnostic information from the hard device, but also is allowing the controllers to set the hard devices into maintenance mode. And this program we developed for testing the application software also can be operated on the level of the controller, so that it's not only suitable for the soft controller operated by the engineering station. It can be operated on the level of the controller, and then you can use this in order to automatically test at least the electrical part of the field instrumentation. Of course, you cannot electrically test the, let's say, the functionality of the hookups of a pressure transmitter, but the entire test as far as electrical functionality, the entire rest of the system as far as electrical functionalities are mentioned can be automatically tested. And again, that means we have the test program, because based on the safety requirement specification, we know what are the test values for each individual device. These test values are forwarded to the safety engineering station, are executed on the controller level, and if the execution is completed, the validation evidence will be provided and will then also be stored in the engineering platform. To give you a flavor, we just implemented this first time for something like 500 safety-related field instruments, and the complete test of 500 instruments, testing 5 values per instrument, took exactly 4 hours. right? And if you do this manually, you typically will require a little bit longer time. The other thing here that is important, you can be sure if you have the test program and you have the validation evidence that all the tests are really executed. Because I got told it should have happened in the past that even instruments got positively tested that were not installed yet. But of course, this is most probably just gossiping. Yeah, last but not least, using the OPC interface of the safety controllers, we have the possibility to directly feedback the process activities. That means, of course, we can do this via the process control system, but we also can do this directly from the controllers to the platform. And here the question just is how much money you want to invest into the configuration of the historizer of your DCS. From a technical point of view, we easily can directly forward the information from the safety controllers directly into the database of the safety engineering platform. Based on that, getting back to where we came from, we have the possibility to provide to you a complete concept using IoT technology, helping you to implement a homogeneous safety engineering, having the possibility to operate a cloud-based safety engineering tool, because what I did not tell you yet, but the engineering platform is done in such a way that it can be implemented in a cloud, so that also for multiple locations you can simultaneously work on this platform. We developed a secure handover of configuration data, and we have the possibility to really fully integrate here OPEX and CAPEX related activities. And all in all, that means that we probably will not be able to replace the hand crank by a regular motor, but it's something like an automated step sequence drive that we can use in order to adapt the safety system in an adequate fashion. Just to give you a final overview, so we have a lot of functional safety management activities. In the past, this was been done either manually or by a conglomerate of different tools. What we provide here now is a safety lifecycle management platform using a database for all the information processing, having the safety-related engineering tool in the middle. You may now ask, what is the consequence of that? Practical experiences have shown that we have time savings for completion of the SRS, which are in the range of 30%, and man-hour savings for the overall maintenance of the safety lifecycle that goes well beyond 70%. Finally, there is only one way to avoid criticism, and I'm well aware of that what I presented during the last 45 minutes, of course, may cause some questions, but I would be more than happy to answer your questions and to enter into a discussion to which extent these ideas and these concepts are interesting for you or not. Thank you. Mark.
So you're saying IoT in this presentation. And but when I went through all this as well, Michelle, and when I think of IoT, as it stands today, IT is our IT folks are rolling out an IoT solution, and it's based upon one of the cloud providers' IoT platform. And folks will come up with an idea, have some certain and they'll deploy some sensors, connect to this device, data goes to the cloud, analytics, and all that. But it's totally unrelated to safety. And they're using
Well, we have in Germany an extensive discussion on IoT and what is the meaning of IoT especially for the chemical industry, for the process industry. And current understanding over in Germany is that as more discrete a production is, as more useful IoT on production level is. That means if you are producing bolts, it might be a good idea to have the possibility to identify each individual bolt and having the possibility to manufacture individual bolts, right? Now, if you are talking about the process industry, let's say a refinery, it might be an interesting undertaking to identify each liter of gasoline on its way from the crude oil to the gas station, but the commercial value of that might be questionable. So a statement I would like to make here is at more homogeneous a production is as more or as lesser useful the IoT principles are for the production processes as such. Now, this is one part of the story. The other part of the story is we, of course, also have to look at engineering and maintenance. And in the areas of engineering and maintenance, the principles of IoT can be very helpful, even if you run things like ethylene units or something like this. Because even though you may not touch the functionality that often, the installations are huge. You have a lot of instruments and devices, and that makes it complicated and that makes it hard to keep an overview, right? So for this kind of things, IoT principles or the application of IoT principles may help you to drive efficiency. And both are IoT aspects. The production aspect and the implementation on production level, but also the implementation on engineering level. The same as if you look at digital twins. I got reminded yesterday that digital twin could mean the digital representation of a product, right? I was on the setup that a digital twin is a digital representation of a device, such as a transmitter or such a controller or something like this. Both is true. And so from this point of view, probably in the future we need to define a little bit a different naming here, or naming convention here. But from my point of view, based on where we stand right now, engineering as well as the real products are exposed to the same naming conventions. And in fact, there is let's say an overlap coming up, because I'm relatively confident that even in areas of the process industry, the future will bring us more individually tailored products. And in order to be ready for that, I think probably not for units like an ethylene plant or a refinery, but for a lot of other chemical plants, it will be also a very important aspect for the future to be able to apply adaptations. And we have in Germany, for instance, this MTP initiative where we're talking about how to structure and how to modularize complete plants so that you can easily create new production facilities without entering into basic engineering from scratch. And this is also something that is, of course, supported by this philosophy, because you can here say, okay, I have a dedicated module, I have all the engineering documents related to a dedicated module, and if I'm combining different modules, the related functionality can be assigned automatically, right? But these are what I'm talking about now are developments that are underway while we are talking. We are actively participating in these discussions and trying to develop concepts that we introduce to our clients so that we can enter into a discussion to which extent the sort lines we have may make sense or not, right? That means what I have been talking about here is something you can get if you like, We implemented the first projects following these principles, but of course we would be more than happy to understand, are there areas where we should do different? Are there areas that make sense? Are there areas that are useless? But I think as this is here called a workshop, it's not only such that we should talk about things that we do since 25 years, but my understanding is that we also are invited to present new ideas in order to evaluate what are areas for improvements. Do you have further questions?
What do you recommend would be the different intervals to run these process checks?
Well, there are 2 or 3 different sequences. One is the management of change. The management of change process you have to go through whenever you are changing something in your safety settlement. Then there is the maintenance task, and the maintenance task is done whenever maintenance is required. And you have the recurrent testing, and the recurrent testing is a task that is done in intervals specified during the safety requirement specification. And the intervals are widely depending on what kind of instrumentation you choose, what kind of functionality you have, and what is the application. Yeah. And this KPI monitoring is continuously done, right? Of course, as long as the data inside the platform are not changed, then the KPIs reported back are the same, right? Okay.
So this product, I understand, is that a fully released product?
Yes. The colleagues from Mangan Software Inc. are sitting here. They also have a booth over in the demonstration area. So if you would be interested, I'm relatively confident the colleagues would be more than happy to talk about further details. Okay. So thank you very much. I hope my presentation was not too boring.